Okay, hi, I'm here to talk about the Lustre iRODS connector. It has some things in common with Robinhood, but we're solving a very different problem than what Robinhood is solving. iRODS is a data management system used throughout the world, and we've had needs to integrate Lustre with iRODS, and so that's what this connector is doing. A little bit about iRODS. iRODS is an open source BSD3 license. It's distributed. You can run iRODS on your laptop. You can run it on a cluster of thousands of computers. It's metadata driven. We like to say that everything is actionable through metadata. You can drive your workflows through metadata, so metadata is a very important feature in our system. It's data-centric, so actions depend on the metadata in the system. First off, I need to back up a little bit and talk about the metadata in iRODS. iRODS does have system metadata, like you see in Lustre, but a lot of times when we're talking about metadata, we're talking about user-defined metadata, and that's a big feature that iRODS has. Users can attach metadata to any of the first-class objects within iRODS, the data objects, collections, users, everything can be attached to metadata. And the system can also, through the rule engine, can automatically attach metadata to data objects depending on, or collections or anything, depending on what's in the files, whatever you need. Okay, so we'd like to talk about iRODS as an integration layer. So iRODS integrates your existing storage, your compute resources, maybe your indexing services to your iRODS clients. The iRODS clients we have iCommands, which are command line interface into iRODS. WebDAV, we have web-based interfaces so that users can navigate all their collections, data objects through iRODS, through the web. Okay, the most obvious thing that you'll see in iRODS is virtualized data virtualization. And what we like to say is that we abstract all your data in your system from the user and gives it a common namespace, a virtualized data system, so that the user doesn't have to know the intimate details about all of the data within your system. It could be just a Unix file system, Lustre, could be object stores, web server, Amazon storage, things like that. And the user doesn't have to know the details about the storage or the replication within the system. So as we say, we provide a logical view into the complex physical representation of your data. So here's an example of the data virtualization. Within the box, you see that we have kind of our virtualized file system within iRODS, the virtualized namespace, and underneath it, you see a bunch of iRODS servers. One of the servers is a catalog server that has a connection to the iRODS database. You can now have multiple catalog servers, and then resource servers as well. The example we show, we have a data object, which is basically a file. We call them data objects, just within iRODS, that has replicas, 3 different replicas within the system. Users can see those replicas, but they don't have to. They don't have to know when they're getting or putting a file where the replicas are going, or where the files are going and being replicated. So we like to say we project the physical namespace into the logical. Another thing is the replicas provide durability and locality of reference. So if a user is connected to a certain resource server, iRODS has resource servers. Each of them have one or more vaults underneath them. And if a user is getting a file, locality of reference is usually the primary decision maker of where the file is being gotten. But also it provides fault tolerance as well. The other thing is data discovery through metadata. So one thing we've discovered is when you have millions and millions of files, researchers and institutions need to be able to find the data files that they want. Having file names and putting things in a certain directory just isn't enough when you have millions and millions of files. So we can put metadata on these objects, and that allows you to discover what you have. And the metadata can be generated automatically based on what is in the object when it was ingested. Basically, the rules that you have can automatically populate metadata on the file. And metadata can be attached to any first-class object within iRODS. So not just, I talk a lot about data objects because it's the obvious one, but collections, users, storage resources, even your zones can have metadata on them. And metadata makes everything actionable. Your rules are generally driven by what is in your metadata. So you can assign metadata to a resource that says what the capabilities of that resource are. So here's an example of an iRODS system with the metadata on the resources, metadata on the user, collection, and files. So an example would be metadata on the resource could tell you what capabilities are in that resource. Is it a high-performance computing, with a lot of compute nodes? Is it a HIPAA-compliant resource? Your policies can be different for that, and the metadata on that resource can tell your rule engine how to treat that data. It could be long-term storage resources, things like that. So I'm giving an overview of iRODS first, just to let you know, and we're going to get into the Lustre connector and how this all connects into Lustre in a minute. Okay, the rule engine. iRODS has a rule engine basically that it's basically a scripting language that when you get policy enforcement points are executed within iRODS, you can write code at the point of those policy enforcement points to do whatever actions you need to do. So you can control authentication, you can control where things are stored, and there are policy enforcement points for basically all actions within the system: authentication actions, storage, any kind of database access. So the rule engine originally was a specific iRODS native rule engine language. Now we support many different languages: Python, C++. So if you want, if you want speed as your main concern, then you would write your rules in C++. So again, the iRODS rules can do really anything, but common things are restrict access to objects, logging for audit purposes, reporting, provide additional context for the objects, and even like send a notification that someone ingested some file in a certain location. We have policy enforcement points. There always have a pre and a post policy enforcement point, and so you can attach your code to those locations and do whatever you need to do at that point. So here's another example of a policy enforcement point of doing a data object put. And when you put that data object, you'll run the data object put pre and then data object put post. But that operation will expand into a few hundred policy enforcement points. So you can, depending on what your need is, you can catch any one of those policy enforcement points and do whatever it is you want to do. If you don't want to do anything, they're just no ops. They won't impact your performance at all. Okay, collaboration. Different institutions can collaborate with iRODS and connect their clusters together. All you need to do is share a secret key, add some users to connect users in the system, and permissions, and they can start collaborating. And then you don't need to pre-plan any of this. They can just, as needed, you can set up the collaboration and then tear it down whenever you're done. So we like to think of iRODS as a interface layer to your storage, to your audit services, your indexing services, your metadata, your compute resources, your authentication resources. It's very easy within iRODS to, storage is kind of built in with different storage plugins. The audit services, we have an audit plugin that will basically write out all the policy enforcement points that you execute. And by doing that, you can audit everything that happens within your system. You can write it to a database, and that helps you know what's going on in your system. Maybe for compliance reasons, you have to have that audit. Indexing so you can find things easily. And these all can be added on to iRODS very easily, just a few steps. Here's another example of federation within iRODS. So we're federating multiple zones, and they're sharing not only data, but they're sharing all the services underneath. So an example would be that one institution needs to do compute on resources from another institution. So you can send the data from one institution to the other institution that does the compute and return the results. Or you can integrate other services between the different institutions. Okay, so this is basically kind of end-to-end, like telling the whole story about the data. That's what iRODS gives you. Anything from metadata ingest to publication to retention. One thing we have, like a lot of government rules around retention policies on different research. Like in England, all the research data has to be stored for 10 years. And sometimes, in some cases, even has to be stored 10 years after the last access of the information. So the iRODS rules allow you to kind of work through that life cycle through the system. And you can add a persistent identifier to all your objects through metadata, and so that you can track what has happened through the system through time. And here's an example of iRODS. Objects are landed in the landing zone and put on a resource there, but those are tagged with metadata that says they need to go to some compute services. So they're sent to a compute resource, and where it has a high performance computing in it, and that can compute results, add metadata to the results, and send it back to iRODS. Okay, so that's kind of a general overview of what iRODS is. So now I'm going to talk about the Lustre framework, the connector is what we call it, the Lustre iRODS connector. So One thing we found is users want all the features of iRODS. A lot of our users have Lustre and they have iRODS, and they want to integrate those two together. They want to keep the features of iRODS, but also keep native access to their Lustre systems. Now, iRODS already supported Lustre as far as a vault, which is a storage within iRODS. Any POSIX system can be your vault. So you could always have Lustre system as a vault within iRODS. But that has some drawbacks. One is that iRODS, when you put something directly in a vault, iRODS wants to be the manager of it. So it doesn't want people to change all the files underneath the file system. It doesn't know about them if you don't go through the iRODS APIs. So that's not, for a high performance parallel file system, that's probably not what you want. You want to be able to have users have direct access to their file system and just let iRODS know about all the changes that happen. Also, you don't want to have to necessarily rewrite all of your clients to use the iRODS APIs. The thing we solved with the connector is you can connect directly to your Lustre file system. All your computing, everything can be directly in Lustre, and we'll ingest those changes within iRODS and attach metadata to everything that you want. And so users can use the iRODS APIs when it's advantageous to them. You know, if they want to search for data through metadata, they can go through the iRODS APIs, but they don't have to use the iRODS APIs all the time. So we'll detect changes. The design of it is users can directly access their file system. We use the Lustre changelog, similar to Robinhood, to keep iRODS in sync with the Lustre file system. All catalog updates are in place, registrations, which means that we don't copy data. We're not in the data path at all. So we will not impact anyone's performance. We just register the changes within the database. Efficiency considerations that we considered when making this connector is we accumulated and aggregated changelog updates so that we send fewer information to the iRODS database. It's multi-threaded, meaning that once we've accumulated the updates, we send the updates to iRODS. We send batch updates to iRODS, and then iRODS, each thread can send to a different iRODS server and wait for a response. We have all the dependencies worked out so that all the updates, even though it's multi-threaded, the updates will still be performed in an appropriate order so that iRODS database is all updated appropriately. So we have a plugin within iRODS that will receive these batch updates and do batch updates to the database. So we can scale with multiple iRODS endpoints. The key there is you want a database that's distributed and so that you can make multiple updates to multiple updates to multiple iRODS servers that all connect to a distributed database. Otherwise, if it's just one database, a lot of times that's your bottleneck. So here's kind of just a little overview of what we do. So we read Lustre changelog. We have a poller of the Lustre changelog. We aggregate the changes and have multiple threads that send updates to multiple iRODS servers. And a plugin that's sitting on iRODS that are receiving those changes and making the appropriate updates. Okay, the iRODS API plugin is a dedicated plugin within iRODS that accepts the bulk updates. There are two different modes for the iRODS API plugin. One is direct mode and one is policy. I talked earlier about all the policy enforcement points that are executed within iRODS. And if you have policy enabled, you will go through the iRODS API and do registrations within iRODS, and that will force all the policy enforcement points to execute. If you have direct enabled, then you're just doing direct database updates within iRODS. So that is the case where you want to prioritize efficiency over policy. So you're just doing batch updates to iRODS. So here's a little quick example of using the connector. First, I showed just mounting the Lustre file system on the server that has the connector. The iRODS server that has the resource that you are defined as the resource for that connector, or resource for those Lustre files, also has to have the same mount point on it. So if those aren't the same server, you have to have the mount point on both the resource and just the one resource, not all the resources, but one resource and the server that has the connector running. So what we do here is we mounted the file system. I left out a few steps of running the connector as a service. And then I just created a file. I did a quick ILS and showed you what was in iRODS, the in-temp zone Lustre DR1. There was nothing there, and then a second later I did another ILS, and you'll see that the file has been registered in iRODS. I can get, through iRODS API, I can get the file information. I can also list the metadata on the file. The Lustre identifier is one of the metadatas that the connector automatically writes so that it can track the Lustre object to the iRODS object. Then I move the file within Lustre, and I do another ILS, and I see that the file's been moved within iRODS. The file hasn't been moved. The file has been registered at a different location within iRODS. ILS, I didn't talk about that. iRODS has iCommands, which are very similar to Unix commands. ILS, iPut is like a FTP put, things like that. There's probably 40, 50 iCommands that let you interact with iRODS just through the command line interface. Okay, here's an example of the Lustre configuration. I mean the configuration of the connector. So a couple things that this demonstrates is that some things that Lustre specific things that we have to give the connector is the MDT name, the amount point that's available to iRODS, so that when iRODS interacts with the objects, it has to know where to find them on the system. The registration point in iRODS. So right now we map all, iRODS has a logical namespace and path. So we map all of the physical paths directly from the mount point to the registration point within iRODS. In the future, we want to make that a little bit more flexible so that maybe objects that belong to certain users can be mounted to their, or can be registered in the user's home directory within iRODS, and also add some user modifications within iRODS so that we can maybe directly map a user in Lustre to, on the file system to the user in iRODS. That's not been done right now. So right now everything is registered at a specific location. But then you can then assign, give it access through the iRODS APIs to different users who are using the iRODS APIs to access these objects. And also just show that we have multiple iRODS endpoints. So you can set up any number of threads that will do the updates. Each of those threads can be assigned to a different iRODS endpoint, so that you can scale horizontally when you're running the system. Okay, I'm going to change topic a little bit and talk about the automated ingest capability in iRODS. This is not specific for Lustre, nor does it use the Lustre changelog or anything like that. We also have a tool that does a parallel walk of file systems, determines differences between those file systems and iRODS, and does registrations within iRODS. And so this has two purposes. One is onboarding your existing data into iRODS, and another is disaster recovery. Let's say you're reading the changelog for your Lustre files, and you want something goes down, something doesn't work, you missing changelog records or something because something crashed. Then you can run this automated ingest capability to synchronize your iRODS registrations with your Lustre file system. And we've run this with distributed database, Cockroach DB, and have gotten really good performance out of it. I have not yet connected the iRODS connector to Cockroach, but that is the next step that we're going to do. Okay, so the key here is for performance, we wanted to make everything parallel front to back. Obviously, we have a parallel file system. iRODS, we have multi-part data transfers that's coming very soon. Can allow you to transfer files in parallel. We now have plugins for distributed databases, specifically Cockroach DB. And we also have the auditing and indexing framework. Okay, so Cockroach, that was the latest database plugin that we've written for iRODS. It's a distributed database, but it supports an SQL-like interface. With Cockroach, you can now have multiple catalog service providers. The catalog is the resource within iRODS that has the connection to the database. That used to only be one resource that could be the catalog service provider. But with Cockroach and some changes within iRODS, you can now have multiple catalog service providers. And that's really important for the Lustre connector, because if you don't use a distributed database, then that's your bottleneck. You can send batch updates to 10 different resources, but especially if you're doing direct access, direct database updates, they all have to be redirected to the catalog service provider. So you really need multiple iRODS, iCat servers to get the full horizontal scaling of the system. Let's see. Okay. I was going to do an online demonstration, but it wasn't really going to be possible here. So I updated the slides just to kind of show you a quick demo of the use of the connector. So in this example, I have a Lustre mount point. I copied 1,000 files into Lustre. I did a couple ILSs just to show that the files are there, are registered there, and the collections are registered within iRODS. And I did a command called iQuest, which is kind of an SQL-like query to query the iRODS database, and just to show that I have 1,000 data objects within iRODS. And that happens just very fast. Okay, another example is I enable the policy instead of direct database updates. I enable policy so that all the policy enforcement points are executed within iRODS. And I updated an iRODS rule, the AC postproc for file path register, which is all the files within the connector are registered within iRODS. So I updated the rule to read out image metadata on the files, or the image information from the file, and write it to iRODS metadata. It's not the best example because I'm doing an MSI execute command, which runs a external Python process to get the metadata from it. In a real system, I would use the Python rule engine and write everything directly in Python or C++ or whatever. But I just wanted to demonstrate that, this just a demo on how you can automatically get metadata from objects that are ingested in iRODS. And then I did I copied a JPEG file into iRODS, and then I did an imeta ls command to see to look at some of the metadata that was in iRODS. So you have some image metadata information, and the Lustre identifier as well. And that's it. Any questions? Yep.
Do you have any questions?
So I'm curious if you've got a general concept of how fast you can read changelog entries?
We do not right now. It's being tested at the moment at the Texas Advanced Advanced.
Heck.
So most of my development was just on VMs, so it's not really a good test on the performance.
And then looking at your config, it looks like you thought MDTs were tied to mount points, but MDTs kind of aren't tied to mount points if they're multiple in a file system. Do you care about that? So with D&E, we can have multiple MDTs in one
right.
mount point. Do you deal with that?
No, but that is something we want to look into and make sure that we can do that. That's actually something I was looking into the other day.